So, welcome. Last time we got pretty much to this level where we talked about motion graphs, and basically the point we made was that if I take just three generic graphs, position versus time, velocity versus time, or acceleration versus time, I can ask myself, what does the slope mean and what does the area under the curve mean? And basically for the coordinate versus time, basically the slope is the velocity, and area has no clear meaning. And then for the position, velocity versus time, the slope is acceleration, and the area under the graph gives you the displacement. And for an acceleration versus time, the slope is what we call jerk, and the area under gives velocity. So they're kind of useful. They kind of like talk about each other. Here's a family. Well, not here's a family. Here's three individual graphs. First mistake, most people, that when people make a mistake, the mistake they make is that they don't register what the axes are. So if we've been talking about position versus time, say in a graphic, in an equation, it's amazing how many people will answer this graph as if it's a position versus time, no matter what I show them. And if we were talking about a velocity question, they'll just look at the graph and say it's velocity. So my advice, especially when you begin, is that you watch out for that. Set an alarm. And I've seen people highlight whatever the axes of the graphs are. And I think that's a really smart thing to do, because you don't want to throw points away just because you simply misinterpreted what the graph was. So watch out for that. Set an alarm. Because they are interpreted very differently. They might look the same, but they're not. For example, if I look at this first graph, then what can you tell me about, well, let's begin. Who's going to volunteer and talk me through this journey? Anybody want to have a go at that? Just talk me through the journey. You start off at 0 meters. What happens next?
You go 20 meters per second over in a positive direction.
Yeah, I go positive for 20 meters at a constant velocity of plus 20 meters per second. You know, same thing, yeah. And then what happens?
Then you stand still.
I'm stationary for 1 second.
And then you go another 10 plus 10 meters per second in the positive direction.
I continue moving in a positive direction for another second, now at 10 meters per second.
And then you change directions.
Then I change direction or turn around, and I travel at a constant velocity for another 2 seconds. What's my velocity at this point?
Negative 60.
It's going to be minus 60 in 2 seconds. So what is it? Minus 30 per second. And then I stop, and then, yeah. Okay. Let's try and talk our way through this next one. Well, I don't know where I start. I'll tell you that, because that 0 is not a position. In fact, there's no positions on this. And I don't go at a constant velocity. I have a constant acceleration. So I do move in a positive direction because it's all positive velocities. So I travel in a positive direction at a constant acceleration of 2.5 meters per second per second. That's that bit. And then, while continuing to travel in a positive direction, because my speed is still positive, I travel at a constant acceleration of, that's going to be 10 meters per second every second, until I reach a maximum speed of 15 meters per second in the forward direction, and I coast. That means travel at constant speed. I coast for a second at 15 meters per second. And then I don't turn around. I'm still going in a positive direction because my speed is still positive, but I reduce. I have a negative acceleration. Positive velocity, negative acceleration means I'm slowing down. I slow down with a negative acceleration of minus 50 meters per second for the next second, and so on. That means stopping. Stationary means you stood still. That means you're traveling at a constant velocity. Completely different interpretation. That means you turned around. That means you turned around. That means you returned home. When those two areas balance each other, I returned home. Positive displacement, negative displacement. Completely different interpretations. So you've got to watch out for that. And then there's a couple of little tricks. Not tricks, but there's a couple of little things that are... I can ask you some numerical questions on this. Let's get rid of that. And so a numerical thing I can ask you is, what is the average velocity between t equals 1 second and t equals 6 seconds? And what you remember is that my average velocity equals my final position minus my initial position, divided by my final time minus my initial time. Sorry, I wasn't going to miss that bit out. Graphically, I'm starting there and I'm ending there, and the average velocity means I'm just doing it in one smooth journey. So I have two ways of interpreting this. I can say, oh, look at my graph. My final position is minus 30, minus my initial position is plus 20. Notice how I put the actual value in parentheses, because that negative is not a subtraction operator, it's an address. And then I divide it by my final time is 6 minus my initial time is 1. So this is 30. So minus 30 minus 20 is minus 50 over 5, which equals minus 10 meters per second. Yep. Or I could say, oh, it's basically, well, we should say rise over run, but this rise is falling. So that's minus 50, and my run is 5. So you can say, oh, my equals rise over run, which equals minus 50 over 5, which equals minus 10 meters per second. Same answer. Two different ways of getting it. Oops, I didn't mean to do that. So can you see how it's great? I mean, it's so useful. I could say to you on this one, what's your displacement resulting from the first, between 1 second and say 4 seconds? So you've got to interpret that. It's a velocity time graph, so it's the area under the graph. And you've got to divide it up into bits. This is not so well done, frankly. And I look at that and I say, that's a trapezoid. I look at that and say, that's a trapezoid. I look at that and say, that's an area. So I would say my displacement is equal to 1/2. The left-hand side is 2.5 plus the right-hand side is 5 times the separation, which is 1. That's the first little thing. Then the next one is 1/2. The left-hand side, which is 5, plus the right-hand side, which is 15, and the separation is 1. And then the third bit is a rectangle, so it's just simply going to be 15 times 1. And so I say my delta x is equal to, 7.5 divided by 2 is 3.75, I think, plus 20 divided by 2 is 10, plus 15. So if I did my math right, that's going to be, let's have a look, 28.75 meters, and it's positive because it's above, it's all above the axis, so it's all positive. Yeah. So those are the skills. It's kind of like some linguistic skills, some conceptual interpretation skills, but then there's a couple of math things at the end where, you know, can you work out the slope? Can you work out the area under the graph? If I give you the equation for this line, I know you can't do it for straight bits, but if I give you a nice quadratic, I think most people will just gobble it up. It's no problem. But if I give you that shape, people tend to struggle with it because I think it's so long since they've done it. But so I'm more likely to give you that, aren't I? I mean, if everybody's getting it right, it's kind of like less interesting to me. I want to find out. I'm not going to ask you impossible questions, but if there's something that I think we need to focus on, then, you know, as a teacher, I'm going to kind of stand around and say, well, maybe that way. Not guaranteed, but maybe. If I get time, I'll ask you both. But questions? So what is the object's direction of motion at t equals 6.5 seconds? Whoa, position versus time, okay. What is the object's direction of motion at 6.5? So what is it? Negative, because it's a negative slope. In this graph, that means the velocity. So it's neg. What is the object's average velocity between 1 and 4 seconds? So you go down there, and 1 and 4 seconds, you go there. It's going to be the rise, which is going to be plus 20. And the run is 3. So V is equal to rise over run, which equals plus 20 over 3, which equals, what would that be, 6.66 positive meters per second. When does the object stop for the first time? What time? What time does the object stop for the first time?
1 second.
It's 1 second. It's that beginning of that guy. So that's 1 second. What is the object's instantaneous velocity at t equals 5.5 seconds? So it would be the tangent to this.
0 meters.
Yeah, 0 meters per second. Cool. I want to go back. I want to go back to, no, I want to go, yes. I want to go back here because I want to ask you a question. Because I want to make sure there's no misunderstanding about this. And that is say, okay. Sorry, I'll get there in the end. On this velocity versus time graph, I'd like to know, after the start of the journey, at what time do I have zero velocity again? Or what time would I, if only for an instant, be stationary? We tend to think of stationary as being you stay there for a long time. But you can be just, you know, it's instant. When I throw a ball up, it's stationary for this split second at the top.
6 seconds.
So that's the point I want to emphasize. It looks 4.5 roughly, but if you look at it, look at that. You're starting there, you're ending there. It's not symmetrical about the axis. The way you do this is you say, I'm going down by 1 step, 2 steps, 3 steps, 4 steps, 5 steps. And I've gone 3 of them down to get to my answer. So I go across by 1 step, 2 steps, whoops, I'm doing the right thing, 1 step, 2 steps, 3 steps, 4 steps, 5 steps. And it must be on the 3rd step that I cross that line, because it's a straight line. 3 out of 5 down, 3 out of 5 across. It's a straight line. 3 out of 5 of a second is 0.6. So I wouldn't accept 0.5. I'd say 0.6. Now, to forewarn you, I'd say, what is the exact time? So that, oh, I gotta get that exact number. So I'll try and warn you about it. I might sometimes do that when it's not a fraction, just to, but I don't want to not do it when, I want you to pay attention, especially at the beginning. Okay, everybody clear on that? Let's look. This is a velocity versus time graph. What is the object's direction of motion at t equals 4.2 seconds?
Or actually positive.
Well, my velocity is positive, so that must be positive. Do you see that? So now I've got a different graph. It's velocity versus time. So rather than the slope for the velocity, I just look at the actual numerical value. Numerical value is a positive value, so it must be a positive value. What is the object's average acceleration between 2 and 7 seconds? 2 and 7. Acceleration is the slope. My rise is minus 20. My run is 5. My acceleration equals rise over run. I'm rushing a little bit. Normally I'd write out, which equals minus 20 over 5, which equals minus 4 meters per second squared. When after the start is the object's velocity 0? There. Yeah. So not 4, not 4.5, 4.6 seconds. T equals 4.6 seconds. Yeah. And as I say, in my test these days, I'd say exactly when. Just so there's no misunderstanding on this thing. It's not that all of the times you can approximate, it's just that I want you to be really careful about that. And then what is the object's average velocity between 2 and 4 seconds? So there's 2 and there's 4. And this is position versus time. So what is the object's average velocity between 2 and 4? So again, I'm doing... Now, tell me what was going through my head. I thought this was an acceleration versus time graph because we've done a position versus time. We've done a velocity versus time. So in my head, I'm going, it's going to be an acceleration versus time. So I was about to do the area under the graph. And then I looked at my axes. That's after 20 years of training, So this is not something where, only an idiot makes that mistake. Well, maybe, but if so, I'm part of the club, It's like, so set alarms. This is, walk carefully here because there's a common mistake. And so this is going to be rise over run. So this is going to be that's going to be to there. That's going to be minus 10 over 2, which is minus 5 meters per second. But I didn't have a sign on this. Oh, that's not good. If I said speed, that would have been all right. But I should. Oh, it's positive. No, what am I doing? I did that the wrong way around. Rushing, rushing, rushing. Rushing is the worst thing you can do. Okay. And then when does the object stop for the first time? Well, when does it stop for the first time?
3 seconds.
Position versus time, yes. Stops for the first time at 3 seconds. Yeah. Cool. Oh, I could have asked you to use your clickers. That's it. Okay, let's stop there. So.